So this is 9.5, section 9.5 on hybrid orbitals. It's hard to imagine tetrahedral, trigonal, bipyramidal, and other geometries arising from the atomic orbitals we recognize. So take a look at this picture. You can see the S sublevel is spherical in shape. Then you guys know the best picture of this, of course, would be the PY. So the PY here, you can see it's a dumbbell shape for the P's. This is what we've known since chapter 6, but we're going to change it up. What we're going to do is we're going to average them all together because we know that something like carbon, we know carbon has 4 single electrons around its outside. It bonds with 4 bonds, whether that's 4 single bonds, 1 double and 2 singles, 2 doubles, 1 single and a triple. Like any combination of those 4 bonds, we know that it bonds, but this does not explain, these shapes does not, it's not a good explanation. And as it turns out, with the geometry of it and the math of it, they came up with something a little bit different. So take a look at this. So this says for hybrid orbitals, take a look at beryllium. Beryllium has 4 electrons. 1s2, these are considered core electrons, so we don't have to consider them at all. Excuse me. No COVID, I'm good. Notice that the 2s orbital here has 2 electrons in it, and then the p sublevel, excuse me, the p sublevel has 3 open orbitals. So what happens? Obviously in this case here, this looks like Be, looks like helium, where the electrons are on the same side, and these electrons like this usually do not bond. So that doesn't make sense, right? Because we know that Be would rather be written like this, where 1 electron on each side, because they want to spread out, and that's exactly what happens. 1 electron moves over to one of the P's. Now, when we have an S and a P orbital that are of the same energy, this is what happens. We end up with 2 orbitals that can bond. They're called bonding orbitals or molecular orbitals. And what happens is the S shape and the P shape kind of combine so that there's a small lobe that comes from the S shape and a larger lobe that comes from the P shape. So what we do is when we have an S orbital and 1 P orbital, we make 2 hybrid orbitals like this. I'll erase the red marks there so you can see it. 2 hybrid orbitals like this, and when we overlap them, you get the smaller part there and the smaller part there. So that would be what 2 orbitals look like, the S, 1s and 1p. So the large lobe of the sp hybridized orbital would have a bonding with, so if we're talking about BF2 like this, I'm sorry, BEF2, then the FP orbital will overlap here with 2 electrons from each, 1 from fluorine and 1 from beryllium, and then the same thing happens on this side. Meanwhile, what you don't see is a smaller lobe like this from this side and a smaller lobe like this from the opposite side. So you don't see those 2 because they're overlapping. The large lobe overlaps the smaller lobe of the other hybrid orbital. So let's just keep going here. So what happens? Again, these are core, so we can ignore them. I have 1s, let me write this out. I have 1s and 1 p orbital, and the other p's are there. And because it's an s and a p orbital and they're at the same level, we call it basically an sp. So what is it if I have 1s and 2p? Well, that would be sp2. So what happens if I have 1s and 3p? Well, that would be sp3. Yes, that's what these letters and numbers mean. I'm going to continue on here. I did exactly what. So here's the sp. Here's the sp2 with boron. Remember, boron is 1s2, 2s2, 2p1. And one of these electrons then moves over here. One of these blue electrons moves over into one of the p. So I have sp2, which is trigonal planar. Good. And then I do the same thing with carbon. Remember, that's 1s2, 2s2, 2p2. But one of these 2s electrons moves here to give us 2s1, 2p3, and all 4 orbitals, the 1s and the 3p, are all at the same level. So now we just call them, so in fact what actually happens is I have 4 orbitals, each has an electron waiting to bond, and this would be an sp3 orbital. This would be an sp3 orbital, this would be an sp3 orbital, and this would be an sp3 orbital. So they've all hybridized to be exactly the same. So these 3 here would be an sp2, sp2, and sp2. I believe this is how it's said. Sp, and this one's an sp. So we kind of consider each orbital here, even though we get, looking back down at the carbon here, even though the first orbital is an s and the second and third and fourth are p's, we kind of combine them so that they're all the same thing, all have the same name, so that you can't tell which sp3 orbital is which. So that's how we do that. All right, let's move on. So hybrid orbitals. So using a similar model for boron leads to, so this, I've already gone through this. The 3 degenerate, this means same energy, that's what degenerate means. sp2 orbitals, so that's 3 orbitals because one's s and 2 are p, look like this. You can see how they go trigonal planar. That gives us, like, they're all on the same plane with those 3. Carbon is sp3, and each one is an sp3 orbital. There. And then you can see how they arrange themselves to look like a tetrahedral with 109.5 bond geometry, angles. So let's just keep going because okay, so what happens when we go past the octet? Because carbon with a tetrahedral is where all octet atoms are. That would be any of those in the second period, and some in the third, like SiH4 is silane, and silane would be tetrahedral because it's 1 silicon atom and 4 bonds, each one to a hydrogen, which would be electron domain geometry of 4, which is tetrahedral. So that would be sp3 also. What happens if we go to expanded octets? So what happens if I have 5 bonding electrons like I do when I have phosphorus that looks like this? That can bond, I don't know what I'm writing there, hang on a second here. That can bond to like a fluorine from each one of these. Now we know 5 is trigonal bipyramidal. So if I have a molecule that looks like this, excuse me, what is the hybridization? Well, I have 1 S, I have 3 P, and I have 1 of the D. This is why, I've talked about this before, this is why only third period and below atoms can have expanded octets. Remember, there's no expanded octets for second period. So this does not, so for the second period, this does not happen. Okay, so it's only third period and higher, or lower, however you're looking at a periodic table. So here I have sp3d1, like sp3d. Okay, that's each one of these electrons I'm looking at right here. Each one of those electrons can then bond, and what I have left then are 4 empty 3d orbitals. Okay, so we can go even one further. We can go to sp3d2, which, we're going to stick with the trigonal bipyramidal. So that gives us 5. What you're looking at here with the big purple or blue lobes are the big lobes, and then there's a small lobe off to the side. And these all look the same: big lobe, small lobe off to the side, big lobe, small lobe off to the side, and so on. Okay? So 6 degenerate orbitals is sp3d2, and that is octahedral. And that's what this is here. So you can see this is sp3d2. Okay? I think that's it for, well, that's it for me.